So, so let's finish lecture 2 today, and let's move on to chapter 3 of the course, the machine instructions. So I think I stopped in at slide 70. 78. Okay, I think I stopped here, right? So I talked about the division. So if you divide a number by power of 2 number, then that can be easily implemented using shift operation, right? As in the multiply. So in this case, it's like if you have an unsigned number, it's easy. You just shift right and you're done, right? But you, in case of if you have a signed number, especially if you have a negative number, then you actually have to be careful, because that's actually has something to do with the definition of division. Okay, so according to in our world, when let's say you divide a number, so if you divide a number, then now you actually have 2 numbers as an outcome. The first one is quotient, and second one is remainder, right? Q and R. Quotient and remainder. Q is 목 in Korean. R is remainder is 나머지 in Korean, right? You know that. So then the question is, what is the right Q, quotient, for division? What would be the definition? So if you have, for example, if you have a positive number, positive n, divider, easy. Let's say you divide positive number 18 by 8. What will be the quotient here? Q. Too easy, right? So if you calculate the number, it will be 2.25, right? But if you take the integer, so our rule is basically you round it. Round this number, you know that this one will be 2, right? So Q is 2 and R is 2 in this case. So more like a subtle question is, what happens if you actually divide minus 12 by 8? So we apply the same logic, then the actual number is minus 1.5, right? You apply rounding. Then what will be the correct number here? There are 2 choices, right? It'll be minus 1 or minus 2. Minus 2? Actually, it depends. It depends on how we define the division. But in case of C, like a C standard, it always defines this quotient should be rounded towards 0. That's the definition in C. Okay, so C language specifies that whenever you actually have some a remainder, some fractional parts, you always have to round towards 0, right? So that means the correct answer here is it must be minus 1, right? Because we round towards 0. Okay, of course, as a consequence, we now have negative remainder, right? Because if you in this case R will be minus 4, right? So that's definition. Okay. You want to implement it, let's say, in this case, to implement divide by 8, we simply this 3 bits to the right, shift right by 3, right? That's it. But if you apply the same logic, let's say, what happens you actually shift this number by 3, to shift right to the 3 bits, then it'll be minus 12 will be if you represent in binary number, it'll be 1 1 1 1. All ones, and the last 4 bits will be 0 0 1 1. That's minus 12. Okay, so this number by 3 bits to the right, then what you get is 1 1 1 1. We assume we do a sign a shift. So 1 1 1 1 ... 1 1 0. 1 1 1 0, because these 3 bits will be gone. Right? So we only have a 1 0 left at the end. So what is this number? If you actually interpret this number, it will be minus 2. So this is not what you want. Okay? It's a problem of shifting, shifting right the negative number, then your answer will be off by 1. Okay? And this part is to correct this thing. Okay? So before you do, if your number is like a negative, let's say original C function, this function actually returns it takes like a signed integer as input and returns the quotient after divided by 8. And if your number is negative, you first make some adjustment by adding like a 7 to it, and then you apply this arithmetic. Okay? Then you will get the correct answer. So that's the reason why if you compare this code with the previous version, so if you unsigned like a division, it takes just only one like instruction, right? Like a shift right by 3 bits. But this one is a lot more complicated because now we actually have to worry about this negative number case. Okay? 네. 네, 라운드 이브는 플로트에서만 일어나는 거죠. 네. 이거는 그냥 예, 정수 나눗셈이니까 네, 어떻게 보면 그 다른 종류의 라운딩 룰이라고 생각할 수도 있겠네요. 네. 라운드 토월즈 제로. 네, 항상 그러니까 정수의 나눗셈에서는 항상 그 몫을 구할 때 라운드 토월즈 제로를 구한다고 생각하시면 될 것 같아요. Okay, so here it's kind of what you already covered, but let's let's go over this basic rules of unsigned and arithmetic. Unsigned ints and whose complement is signed. Like unsigned and signed ints are isomorphic rings, whatever it means. I mean, just like both are groups and one dependence between the two. I mean, if you have like all inside number, elements in the unsigned number, then there will be like a one-to-one simple like a mapping function. Mapping function exists between the two, and that mapping function is casting. If you remember, there was like a function. We apply u to b and b to t. We first take this unsigned number as input and translate it into binary sequence, and then take that binary sequence as input and filter it through like a b to t function. Then we basically do casting, right? We cast unsigned number to signed number and signed number to unsigned number. So if you apply that like operation, that's the mapping function between the two. And shift to left is kind of easy. Shift to left is both like a signed and unsigned number. It corresponds to multiplication by 2 to the power of k if you shift it by k bits. And there's only one version of shift, like to the left, right? Or shift left. You always put zeros in the new position, right? And shift to right is more like a subtle. Depending on the signed integer or unsigned integer. If in unsigned integer it's easy, you can just shift it to the right by k bit to implement divide by 2 to the power of k. But in signed integer, you have to be careful, especially in dealing with negative numbers. I said before, so because if you just blindly apply a shift right function to the negative number, you round away from 0, right? Because your answer will be off by 1, right? So in order to fix that, we actually use biasing. It's like this part. In the previous slide, this is the biasing. In general, this biasing is 2 to the power of k minus 2 to the power of k minus 1. That's the the biasing. In this case, 7. 2 to the power of k is 8 in this case. We take 1 off from it. This one is biasing, and then in that way you can basically calibrate it. We calibrate the number to be compliant with the definition of division in C. Properties of unsigned arithmetic, we talk about a little bit. We only talk about this in the floating-point arithmetic. So, if you remember, floating-point add, forms, the abelian group, and both like a floating-point add and multiply forms a commutative ring because, commutative ring is this set must be must be must form a commutative group with addition, and multiplication. It's defined over operation. Let's say we have set here and addition, and there are two operators, addition and multiplication. Then this one is this actually set form this tuple form commutative ring, because addition is already commutative group. Actually it's an abelian group. And it's closed under multiplication. All this result of multiplication will be mapped back to the original set. Multiplication is commutative. You can actually change the order of multiplication to get the same number. And multiplication is associative. You can change you can group like a two different like a set. It doesn't really have to. You can group which one, no matter which group you actually perform first, the result will be always the same. And there exists a multiplicative identity, which is 1, and multiplication distributes over addition, which is 분배법칙 in Korean. So if all of these properties hold, then now this unsigned multiplication and addition forms commutative ring. And if you consider like Tooth complement arithmetic, which is signed integer, then basically they are isomorphic. So isomorphic means, as I said, there's one-to-one mapping, the simple mapping between the two. So they actually have the same like algebraic properties. Tooth complement is also actually both forms rings, and there exists an isomorphism, which is like a simple mapping function between the two. So they actually have the same like arithmetic properties. Both are rings, and one difference is integer obeys ordering properties. In other words, if if you add the same number to the left and right term, then this one is true for the pure like mathematical integer, like abstract like a integer. If you add term to the both sides of an inequality, then the inequality still holds, right? So it's like it holds in like a mathematical integer arithmetic, but in like a reality, in like our C, like a in real implementation, in our implementation of this arithmetic, it doesn't hold, because there's like there's some like a limited number of bits, and there can be some overflow and wraparound. Then this one doesn't hold, right? Because there can be some like inversion of a sign and so on. So this one actually shows in such example. So if you go over like a Tmax, now it becomes Tmin. So this inequality doesn't hold in our like implementation, and you have to be careful about that, right? So the last slide, which is somewhat odd, but I'm going to explain anyway. So so once you write your C program, that will be compiled into assembly code, right? And if you disassemble like this assembly code, the code generally looks like this. This one is by the way, this is called machine code. This one is called assembly. So there's like one-to-one like correspondence between the two. So if you have like a pop instruction, that will be represented by binary, sequence binary like byte like a 5B. So 5B in machine code means like a pop, EBX register, and so on. So there's like a one-to-one mapping. But in this case, what you want to see is how to represent this number. So for your information, this add instruction, what this add is, read this like a register value and add this constant to it, and then store the result back to the register. Okay, so in other words, this one computes like EBX is one of the registers in Intel architecture. Let's say this register value is updated with original like a value of EBX plus this constant, which was 0x12AB. This is what is this instruction. Okay, and then the question is how to represent this value. This value. So this add instruction, this means like add and EBX register. This information encoded in this like 2 bytes, 81C3. This one encodes this add instruction plus this register. And this part actually conveys the this constant value. So in this case, 1 to 12AB, right? But because this one actually generally add instruction, this one actually takes like a 32-bit constant. Must be first, this number first to be extended to 32 bits, and then we split this 32 bits into like 4 bytes, and then take the little endian representation in this Intel architecture. The LSB like least significant byte will be placed in the lowermost address. So if you see, this instruction starts at address 048366, 366 with 67, 70, and not 70, it's like a 6. Okay, so it's like a 6 bytes will be placed in this, and as we said before, as we already covered this endianness problem. So whenever you place this like a byte, like a word, into like a byte addressable memory, there are 2 choices, like how represent, store this like a word into bytes. The first choice is the LSB, the least significant byte goes to the lowermost address. That's called like a little endian. And the other choice is, the LSB goes to the uppermost address. That's called big endian. And interact like a little endian machine. So this like a LSB. Case AB is the LSB, right? The AB goes to the lowermost address in this case. So that's how this number is in like a real machine instruction. Okay, so this completes the lecture 2, arithmetic. So any questions about what you covered today? Yeah. 그러니까 결국은 우리가 지금 가정하는 거는 이제 그 소위 말하는 폰노이만 아키텍처라고 해가지고 이제 메모리가 이제 코드하고 데이터를 전부 다 한꺼번에 갖고 있는 이제 그런 구조잖아요. 이 프로세서가 있고 이제 메모리 스페이스가 쫙 있어서 거기 이제 전부 메모리 값이 저장이 되는데 결국은 이 코드들도 이제 메모리 로케이션 저장이 되겠죠. 어떤 주소에 저장이 되겠죠. 근데 저게 지금 왼쪽에 있는 저게 뭐냐면은 8048366이라는 이제 있는데 이 명령어가 시작이 되는 거죠. 명령어가 저장되어 있는 어드레스 주소가 있고 거기서부터 시작하는데 이 명령어가 이제 6바이트 명령어죠. 이게 6바이트를 이제 이거를 이제 인코딩 이제 머신 코드로 이제 트랜슬레이트 하면 이제 6바이트가 나오는데 그 6바이트를 저장할 때 요 이제 상수값을 저장해야 되잖아요. 요 명령어 안에 있는 상수값. 요 상수값을 인코딩할 때 제일 그러니까 저게 이제 366에서 시작해서 6바이트에 저장이 되니까 366부터 이게 차지하는 위치가 차지하는 주소가 366부터 36B까지 차지하겠죠. 6바이트 차지해야 되니까. 그래서 이게 이제 366에 들어가고 367, 368, 369, 36A, 36B 6바이트에 이제 들어가게 되는 건데 이 숫자가 가장 낮은 그 값을 그러니까 상수값의 가장 LSB 가장 낮은 값이 이 주소에서 가장 밑에 쪽으로 들어간다는 거죠. 근데 만약 빅 엔디안 머신이었으면 만약에 인텔 빅 엔디안 머신이 이렇게 됐겠죠. 이거 저장할 때 이렇게 됐겠죠. AB 12 00 00 if it were a big endian machine. 근데 in fact this Intel architecture is a little endian machine, so this one is actually not true and it's stored in this manner. 되는 거죠. Okay. Any other questions? 이거는요, 제가 그 명령어 이거 인코딩을 봐야 되는데 여기에 있는 게 arbitrary length 들어간 건 아니고 이거 16비트까지만 들어갈 수 있을 거예요. 이게 제가 기억하기로는. 그래서 16비트로 만약에 인코딩을 하면은 0028이 되겠죠. 그래서 뭐 0028이 여기에 들어가. 아닌가? 이거는 아키텍처 그 아마 그 인코딩을 봐야 되겠는데요. 네. 명령어마다 달라요. 그러니까 명령어마다 이게 여기가 16비트밖에 못 들어간 경우도 있고 32비트 다 들어갈 수 있는 경우도 있고 그다음에 뭐 네. 저거는 인코딩을 찾아보고 아마 그 인코딩 그걸 봐야 될 것 같아요. 테이블을 보고 이게 정형화 딱 정해져 있어요. 이게 예를 들면은 CMP 명령어는 항상 처음에 83으로 시작하고 그 다음에 뭐 따라오는 필드가 뭐가 따라오고 그다음 몇 비트 뭐가 따라오고 이게 다 ISA 그 Instruction Set Definition으로 정해져 있기 때문에 거기에 맞춰서 인코딩을 하는 거죠. Okay? Any other questions? No? Let's move on. Okay, so now move on to the machine level programming because you guys showed some like interest, encode this assembly code into machine code. So now we actually dive into this machine level programming. So here is the idea. So in this chapter, this is chapter 3. So in this chapter, what you're going to learn is how, let's say you write your code in C or high level language. Eventually, that must be translated into like a low level machine level code, right? So we're going to learn for various pattern of program constructs such as like a loop or conditionals or function calls, all these things. We're going to take a look how these like constructs are translated into machine level code. Okay. So in a sense, as I said before, the goal is goal of this chapter is to make you a great human compiler. Okay. So we're going to give you a C code, and you should be able to translate this one into like machine level code. That's the goal, and there will be like four lectures from this week, and those like a couple of weeks after the Chuseok holiday. Over this chapter 3. By the way, the lab 2, like homework number 2, will be out on right after Chuseok. So we decide to give out after Chuseok than before, to not mess up your holiday. Yeah. So second lab will come out on October 10th, Tuesday, right after the Chuseok holiday. And it requires you to write some like machine level code to solve problem. Yeah, it'll be fun. I mean, it'll be a fun lab. So let's start from something like this. Let's start from some like a history of Intel processors and architecture, which is like main primary like instruction set in this course. So like history of Intel processor is like history of CPU. I mean the history of processor like a CPU. So the first processor like a CPU was first, like a silicon, like a microprocessor was in 4000, like 1971, like Intel 4004. So we're going to go over a brief history of Intel x86 processor. This processor actually dominates server, desktop, and laptop market. Okay. Do you know what's the dominant player in mobile, like a smartphone, like a tablet? Intel architecture is widely used. Like ARM, right? So ARM architecture is like is the main like dominating player for like a mobile and the embedded domain. They take like evolutionary design, meaning that they actually have like they maintain a policy of backward compatibility. In other words, the first like a 16-bit processor was introduced like 8086. This processor was introduced like in 1978. It was long before we were born. Actually, but still we can run like these like a legacy code on today's processor. They actually Intel intentionally maintains backward compatibility so that you can run any code written on Intel architecture. They can be still run on today's processor. It's like a huge deal for the market because cost of like a software is really expensive. I mean, once you write a program, you actually your code is running on a certain processor. It's very expensive to replace this software. I mean, because the cost of like software is more expensive than like replacing hardware. So generally, that actually contributes to the market success of Intel architecture. But instead, they keep adding more features, more and more features to the architecture. So now actually they have like a bulky, big instruction set. They only had maybe some low hundreds of instructions in their instruction set. But today they keep adding a new instruction again and again. And then now they actually have more than 1,000 instructions in the instruction set. That's the reason why it's called like a complex instruction set. So the complex instruction set means there are two instruction sets, two styles of instruction set design. First one is CISC, like complex instruction set, and second one is called RISC, reduced instruction set architecture. So they are like opposite. They are like two different styles of instruction set design. And Intel architecture is CISC instruction, so they actually provide many different instructions, like more than 1,000 distinct instructions with many different formats. But the opposite side is they RISC instruction. In RISC side, for example, the ARM ISA, they only provide like around 100 instructions and most. So they only have like a small number of instructions, and then simpler. So let's think about the homework you are doing, right? So you guys writing some division code, or some addition, all these things in software, right? So it's like a RISC versus CISC. So in CISC architecture, there's got these designated instructions to doing for division, for example. But in RISC architecture, maybe there's no division instruction. Then what you can do is basically you emulate this division using software, like simple instructions, right? But if your instruction set is simple, then you can run this CPU really fast, because now CPU is simple. You can run this CPU at more higher clock rate, for example, so that you can do the same with more instruction, but you can execute those instructions faster than like a CISC instruction. So there's two, right? So there are two architectural styles. Besides CISC, you have a lot of complex instruction, division, sine, cosine, even some very exotic functions. Those instructions are provided in native hardware. That's like a CISC style. In RISC style, you only have a handful of instructions, but you can emulate anything using this software, right? But you can run this. The point is, because now you actually have simpler instruction set, your hardware can be a lot faster, efficient. Okay, so there's two different styles. So generally, in historical perspective, RISC machines are, generally, have actually better performance than like a CISC architectures. But Intel, they actually put huge engineering effort to create a CISC machine whose performance is competitive with like a RISC machine. Okay. Then this is a part of the reason why this Intel architecture is not very popular in mobile and embedded. Because in mobile embedded domain, power and cost is such important. So if you actually have a very complex instruction set, then your chip becomes very complex, and it's very difficult to make it efficient. It'll become more complex, and it takes the chip size gets bigger because you have to support all these complex instructions, and also it's very power hungry. Because your chip size gets bigger, then it consumes more power, so it's less efficient in a mobile embedded, which actually has very limited resources for power and budget. So here's the milestones. 8086 first introduced in 1978, which was first 16-bit Intel processor, which is basis for IBM PC and DOS. I don't know if you guys have ever seen this machine. I have seen these machines, but you guys probably haven't. Interesting thing is, at the time, the clock speed, if you buy today, you probably buy a 3 gigahertz, a 4 gigahertz. Time, the CPU frequency was 5 megahertz, not gigahertz, right? It's almost a 1,000 to 1 ratio. So it's much more, and there's no Windows. We only have a text interface. Only you have shell. Okay, that's the only thing you had. 1 megabyte address space because you have only 16-bit, meaning that your word size is 16-bit. Integer is 16-bit, address is 16-bit, So you can only address up to like 2 to the power of 16, which is only like 64 kilobyte. But they actually do some magic to extend this like address space to 1 megabyte. I'm not going to go over the details of it, but that's the maximum address space you can have. That means you can have only like have at most like 1 megabyte of memory in your system. Today you have like 8 gigabyte, 16 gigabyte memory is kind of the norm, right? And 386, first introduced 1985. The transistor count is like about 10 times more transistors per chip. So now actually more hardware resource, and clock frequency also increased to 16 to 33 megahertz. And first, like a 32-bit Intel architecture, which is referred to IA632. So IA632 is the Intel architecture 32. And they actually add like a flat addressing. Flat addressing is, address space is like contiguous from 0 through maximum memory space. Isn't it kind of natural? But previously it was not. I mean, they actually have like what is called segmented address space. So if you have like a 1 megabyte memory, then certain memory space resides starting from 0, and another segment starting from like 10000000, and another space starting from 11110000000. They actually have like certain multi space. So that's like a space, but in this case, they first added like a flat addressing, which becomes the norm, like the standard in like later processors. Pentium 4E, like first introduced like 2004. This was first 64-bit Intel x86 processor, referred to as x86-64, which is the main ISA of this and dominant. Core 2, 2006, first multi-core, like a dual-core processor, and i7, first like quad-core processor in 2008, and so on. This kind of brief history, and this one actually shows the transistor count. Generally, if you have like more transistors, that means more logic, more gates, like AND gates, OR gates, NAND, and so on, right? More memory, more gates, and more logic, more adders, more like multipliers, and so on. So if you see, there are like almost like 1,000, more than like 1,000x increase of transistor count from 386 machine to today's Core i7. Okay, phenomenal. So to use this like transistors effectively, they features added. So instruction support for multimedia instruction. I don't know, you guys have heard about like AVX, like MMX, AVX. Those kind of new like instructions added for processing like a multimedia workload, such as video encoding and video, and so on. And instructions to enable more efficient conditional operations, like conditional move, which I'm going to cover in the slide. So you can execute the move instruction depending on the value of the flag. I mean, if it's true, then you execute it. Otherwise, it becomes no operation, and so on. The condition. This one is basically conditional move. Transition from 32-bit to 64-bit architecture and more core. All these features are enabled by more transistors become available at the same like cost envelope. Okay. What about AMD? You guys know it's very hard to find AMD PCs these days, but like all the around like 2010, AMD PCs were pretty popular. And also, I don't know how you guys interested in PC market. You guys have heard about Ryzen processor recently. Ryzen is kind of new, architecture coming from this AMD, and they historically AMD actually it's like an x86 clone. In other words, they actually build a processor. So if you can run this code in both Intel architecture and AMD architecture, it's clone. I mean, they are compatible. They are compatible. They implement the same based on the same ISA. Instruction set architecture. But AMD has followed just a little bit slower, but a lot cheaper than AMD. So it is pretty popular in value market. I mean, especially like developing countries or like mainstream, like large volume PC. They actually adopted AMD CPU. And then, only like middle of like 2005 and 2006, they actually had like they was ahead of Intel by building like a processor called Opteron. So Opteron is very like well designed CPU came out from AMD, and it became tough competitor to Intel Pentium 4. And they actually developed like x86-64, which is like they actually first introduced like 64-bit extension from IA32 to the market, so that they actually first like dominated. They actually had great like a much larger like market share but recently Intel came back to reclaim the market. So they actually lead this like PC market. Actually they dominated. So pretty much like over like 90% market share over the world. And AMD had fallen behind, but it's coming back. Recently, AMD actually came back with the Ryzen processor, which actually has very good review. I haven't tried it myself, but it's actually has very good review. So and the cost is actually the price is a lot cheaper than the same grade like an Intel processor. So they actually have some like good position to come back to the market. They actually, in a sense, they actually provide better like cost like better performance for the same cost. Okay. And 64-bit history. I mean, again, like this is last slide for the history. So Intel actually, in around like 2001, Intel attempted like a radical shift from IA32 to IA64. But unlike this name demonstrates, these architectures they're not compatible. I mean, they are very different architectures. I mean, in other words, the instruction sets are very different. So, this processor is called like Itanium, which didn't success in the market. Eventually, they tried very radically different like instruction set from the original IA32, which is called IA64, and they actually had Itanium family of processors, but it didn't success. It actually failed. So it's jokingly said like a titanium because Titanic was like collapsed. Some people actually call it like a titanium. It's actually collapsed. But you can execute the IA32 architecture code, but by emulating it. So efficiency is pretty bad, and performance was not very good. So eventually, they actually closed this product line. They actually just gave up. And in the meanwhile, the AMD steps in with more evolutionary solutions. So now, evolution instead of like taking like a radically different approach, they actually maintain the same like IA32 like ISA, but they actually does some like extend to like kind of straightforward extension to the original IA32, like AMD 64, like a 64-bit extension 32, and this one is also called x86-64. So this one actually formed the basis for x86-64 ISA, and Intel eventually they gave up this IA64 and they came back with like what is called EM64T extension, but this one is almost identical to AMD 64. So now eventually they actually merged the architecture x64, and this one is kind of vendor neutral name. x86-64 is kind of vendor neutral name, but AMD 64, EM64T is kind of they are the same, virtually the same, but there is kind of more vendor specific. Okay, so that's kind of the brief like a history. So today's like laptops and all like processors support like an x86-64. Except for very like low-end x86 processors. Okay, so that's kind of the 64-bit ISA x86-64 is the dominant ISA in today's market. Okay. Okay, so this one's like a brief history, and so let's move on to the concept of assembly and machine code. I already explained what is machine code and what is assembly code. Already did that, but let's be more concrete. Let's review. So I talk a lot about architecture, or ISA. Okay, so what is ISA, or architecture? So architecture is the part of processor design that one needs to understand or write assembly machine code. Okay, so you can think of it as like header file for the CPU, if that kind of thing ever exists. Okay, so here's an analogy. So let's say you write your program in C. So let's say you write a program like main function, and there is something, and then you have like a printf here. Okay. In order to use printf, what header function must be included? Header file, stdio, right? You have to include stdio standard.io.h, right? So stdio.h includes the function signature, right? So its function signature means the input-output specification function, printf. So it specifies how many and what types of input must be provided for this printf, and what will be returned as a result of computation. So this header file only contains this specification of the function, not implementation. Okay? So your implementation, the real implementation of this printf function exists in somewhere in the library, which is called the libc. So there's a body is actually implemented like a libc function. libc like a library, like a C library, C standard library. But you don't really have to worry about this libc. You only need to know about this a function signature and the problem of using it. Okay. About CPU, let's say you actually have a CPU vendor A, like Intel CPU. Let's say also like AMD CPU. There are two real implementation of like a CPU, right? But you said there can be common header file such as a CPU.h. Can such thing exist? So this one is basically ISA, instruction set architecture, the common abstraction from different families of processors. Okay, so in order to use this CPU as a programmer, you only need to understand ISA, instruction sets. So instruction sets define what kind of instructions are provided, add, CMP, jump, compare, all these things. What kind of can be run on this chip, on this CPU, and how many registers are there? How many registers? What are those? They are all defined in ISA or architecture, instruction set architecture. In contrast, this microarchitecture is implementation of this ISA. So there can be many different implementations for the same architecture, because as we see, even though these two chips basically are compatible with each other, meaning that if one code can be run on this one chip, then on the other chip too, because they are compatible. Okay, so this is the architecture is about is more is about a compatibility layer between these two families of processors, and microarchitecture is basically how these chips are actually organized inside. That includes how many this pipeline is how pipeline is organized. We're gonna go over this pipeline in the second half of the course, and also what's the clock frequency, running at 3.0 gigahertz or 3.4 gigahertz. This kind of, they are also part of this microarchitecture design. Okay, but from a software perspective, these two CPUs are identical because they support the same instruction set, right? So That is called like a architecture, and microarchitecture is kind of implementation of the architecture, like cache size, core frequency, and so on, like a number of pipeline stage. Code forms, there are two distinct code forms, machine code and assembly code. And machine code is basically ones and zeros, like a byte level program that the processor actually executes, like ones and zeros. And assembly code is a text representation of the machine code, like add, CMP, sub, all these things, like a human readable form of the machine code. So example ISAs include x86, i832, Itanium, x86-64, this kind of Intel ISA, historical like Intel ISAs, and ARM ARM ISA used in almost all mobile phones. That's basically two dominant ISAs available today. Questions? 그러니까 간단하게 우리말로도 설명을 하면 그 IS라는 거는 이제 명령어 세트를 정의하는 어떻게 보면 표준이죠. 그래서 명령어 세트를 정의하는 표준인데 그거를 구현하는 여러 개의 칩이 있을 수 있죠. 그럼 예를 들면은 아까 뭐 똑같은 프로그램이 이제 우리가 인텔 칩 위에서 돌 수도 있고 AMD 칩 위에서 돌 수도 있잖아요. 왜냐하면 그게 수정 없이 그냥 컴파일된 코드가 돌 수 있는 이유는 얘네 이 두 가지 칩이 같은 그 명령어 세트를 지원하기 때문이죠. 그러니까 같은 그 코드를 실행할 수 있다는 거죠. 그러니까 호환이 되는 칩이고 그런 의미에서 그 두 개의 칩은 같은 ISA를 구현하고 있다고 얘기할 수 있고 보면은 굉장히 abstract한 뭐랄까 추상적일 수 있고 구현은 다르겠죠 칩마다 내부 구현은 다르니까 그런 경우는 두 개의 칩은 각각 다른 마이크로 아키텍처를 갖고 있다고 말할 수 있죠. 그러니까 우리가 마치 아까 헤더 파일 아날로지를 하면 헤더 파일에 예를 들면 소트라는 펑션이 있는데 소트라는 펑션이 내부적으로 퀵 소트로 구현되어 있는지 뭐 버블 소트로 레딕스 소트로 구현되어 있는지 그건 다 숨겨져 있는 디테일이잖아요. 그 디테일에 해당되는 부분이 마이크로 아키텍처고 그 다음에 우리가 실제로 겉에서 보는 인풋 아웃풋 비헤이비어가 정의되는 그 스펙 그거는 이제 아키텍처라고 보시면 돼요. Okay? Hopefully it's understandable for you guys. So here is a view of assembly like a machine code, like a view of this machine, like a architectural view. So any like a CPU is nothing but big FSM, finite state machine. 그죠? So if you learn like a logic design course, finite state machine FSM, and FSM is basically every clock cycle you put, and this state moves to the next state and so on, right? And because this CPU is also big FSM, we actually have to first find the state of this FSM, right? So what constitutes the state? So here is the programmer visible state of this ISA architecture. The first one is program counter. So program counter is a register that actually stores the pointer to the next instruction to execute. Okay. So this is a special register that actually contains the address of next instruction called RIP in x86-64. So it's like a rest in peace. But anyway, that's the RIP is the program counter in Intel ISA, and register file. So register file is small storage on chip. You can actually place your data. So there are like some like a finite number of registers, and these registers are called a register file as a group. The conditional code. So conditional code is like a flag register. So once you compute some value, like execute like add or sub, maybe you actually have like a carry came out of the computation, or overflow, or like a zero. All these things are stored in special like flip-flops called like conditional flags or conditional code. So these actually constitute the state in the CPU side. On the memory side, now you actually have like this address. You actually have this memory also constitute your programs like a state, this architectural state, and memory take address as input, and it returns data. If you want to read from memory, you provide the address, and you actually return the data from the address, right? And if you want to write to the memory, you provide both address and data, and your value will be updated at the position, at the location, right? So in summary, this program counter, registers, conditional code, and memory. These 4 components constitute the state of your program, state of your machine. Okay. And by the way, we actually store both. We assume like a stored program architecture, meaning that both program code and user data are stored in the same memory. Okay, so this is the like today's like a dominant concept. We store both program code and data into the memory. So if you want to compile your code into binary, like executable code, let's say you actually have like 2 source code, like a p1.c and p2.c. Then you compile with command like gcc -og, like a p1, p2c, and -op. So what does it mean? So this one is like a optional like optimization flag, like optimization level. So if you actually increase optimization level, generally it takes longer to compile, but the quality of code is better. I mean, more efficient code will be produced. This is like optional, like a optimization flag. And this one are 2 source code. And finally, the output is like executable will be generated in the name of P. So P will be the final like executable like code, the file name. But although it only takes like 1 line, internally there are like multiple different steps. In the first step, the compiler compile your C program into assembly code, right? The assembly code, as you know, is the human readable, form of the machine code, right? So that's assembly code. So it actually, once you compile your program, it generates like a .s file. .s file is basically assembly code. There are 2 modules having like assembly programs, and then the assembler it kicks in to translate this assembly code in machine code, like a ones and. So this one is like a human readable, and this one is not human readable, like an object program. And then finally, there's a special program called linker. So linker actually combines all these like modules into single binary. Okay. So if you use like a Windows machine, there are a lot of C files, like exe files, right? So eventually, exe files are created by linking all different like assembly like modules, like a .o files, into like a single file. So finally, this one becomes executable. This is called like the program that can be executed. And optionally, this program is generated by linking static libraries. Like one example is like a libc. So libc is a basic like a C library that actually include the implementation of printf, malloc, whatever other functions, like standard like basic functions, are all like included in this like a libc library. And then in the linking phase, your source code, if your program actually has printf in it, your source code and this library are linked together to become the single like executable, and it's done by the linker. Okay. So here's the example. Is the example of the first step. Let's say we have like a source code like sum.c, which actually defines like a sum store function. So here's a sum store function, and this plus function is defined outside. Let's say we just simply use it, like it's external function. This one is not defined inside this module, but we actually eventually we call the right function at a linking time, right? We actually just match them together to do the correct behavior. So once you compile this like a function, then this one is like a generated x86-64 assembly, for example. This one actually, it only takes a 6 instruction, like a push some operand, and then move move this like operand to the register. So basically, this instruction does copy this RDX register value into RBX register, and then you call the function called plus, and actually it stores the value, the return value. So return value is stored in RAX register by convention, and this value will be copied into the memory location pointed by dest pointer. So let's say this RBX actually holds like a dest pointer. Then this one actually copies the return value to the memory location pointed to by dest variable, and then it actually recovered the original RBX return. Okay, so this one actually produced this one is like an example, the assembly code generated by this function. But if you use like a different compiler and different versions of compiler, then the produced code may vary. But this one is kind of one example how this code is translated. So in assembly language, there are like a certain constraints, and it only supports like limited data types, limited number of data types. So integer data of like 1, 2, 4, or 8 bytes. So it can be this not 16 or 24 like arbitrary number, but it can only support the integer value of 1, 2, 4, or 8. Okay, it can be like a data value or pointers. And floating point data of 4, 8, or 10 bytes, but 10 bytes is kind of extended, like a floating point which is no longer widely used, not used very widely. So these two are very popular. Like this one is single precision, and this one is double precision. Code, byte sequence encoding byte sequences encoding series of instructions. This like code. And there's no aggregate type, such as array structures. Simply, array and structure is purely like a high-level like construct. And then once you create an array, there's no like struct type or array type in assembly code. You simply put them into like contiguous space in memory, and there's no like a struct or array supported in like assembly language. What about operations? So the assembly instruction perform arithmetic function or on register or memory, and also second category of operation is transfer data between memory and register. This one actually includes like add, sub, XOR, not, and so on. Integer like arithmetic or logical operations can be performed. These are supported in language, and also transfer data between memory and register. In the previous slide, there are like a state, like a register and memory. So there are instructions that actually moves the value of register into memory, copy the value from register to memory, or vice versa, like from memory to register, like this. So you can by the way. Storing register value to the memory is called like a store operation. And copying the value in memory to register is called load operation, LOAD. So this one is like a load, transfer instructions, like a load data from memory into register, store register data into memory. Those operations are supported in like assembly, this ISA instruction set. And transfer control. So let's say sometimes you have to jump to like a different location, or in order to execute a loop, there must be some branch instruction, right? Branch means whenever you reach certain like a point, depending on the condition, you actually jump to the like a remote location or just go to the next instruction, depending on the condition, right? That's called branch. So this is like a branch, like unconditional branch, unconditional jumps or conditional branches, or like function calls and return instructions. So if you see the previous instruction, this one is an example of like instruction, because call is like a function call, right? So you go to the remote like location to execute like a next instruction, right? One or return. Return is another example of like control instruction, because if you execute a return instruction, you have to go back to the original caller, right? You have to come back from the function call, right? So that's basically, example of this control instruction. So these are kind of typical like assembly, typical operations like are supported by this assembly language. So once you actually get this like assembly code, as I showed you in 2 slides ago, now the assembler translates this assembly, human readable assembly code into machine code. Okay, so once you translate it, there were like 6 instructions, if you remember. There were like 6 instructions, right? 1, 2, 3, 4, 5, 6. And these 6 instructions are, this one actually takes 14 bytes. Okay? The first, like a push instruction, only takes like 1 byte. And second, the move instruction takes like 3 bytes. And this one is a move. This one is like a push. This one is a call. This one is move, and so on, right? And this one is like a pop. And this is return. Okay, so like this assembly codes are translated into this sequence of bits, like ones and zeros. There exists like a binary encoding for each instruction. But one thing at this moment, we actually still have missing linkage for this function call, right? Because this like assembler only translate this instruction into assembly instruction into like a machine code. We don't really know where this plus function exists. Okay, so because plus function is defined in somewhere else. I mean, some other file, some other module, right? So still, we need a linker to link like this, like a function call and the function body together. But at the point of like this like assembling, we don't actually have that information yet. There's still like a missing linkage between the different files. Finally, this is linker as a problem. So linker actually resolves references between files. In this example, there is a function called plus, which is like defined in another file, right? In a linker, actually they take like a multiple, and they actually link this like function calls to, so that it comes to the right location. So combines static like a runtime libraries or dynamic linked libraries. So there must be some like code for malloc, printf, and so on. These functions must be correctly linked to be executed. And some libraries are dynamically linked. So there are 2 options of linking. So let's say you want to use library functions which you didn't write. Then this linker must find this function and link them, right, together, like printf. You are not the author of the printf, right? Printf was written by somebody else, but you want to use it in your code. Then you actually have to link it. Then this linker actually does it, but there are 2 distinct flavors for linker. The first one is called like a static linking. Static linking is you basically fetch this like a function body at compile time and put them into a single executable file. That's called static linking. And second is called dynamic linking. So dynamic linking is when you execute your program. Okay? So your binary doesn't include the body for printf, right? But when it happens is when you first execute this call printf, it first actually jumps to the linker, right? And then if you load this code for printf into the memory and link this like a function to the at that like at the time of execution, that is called dynamically linked. If you have installed like a Windows like a system, you probably have heard a lot about like a DLL file. DLL 파일 본 적 있어요? When you actually install Windows, there's some blue screen pops up and DLL file is missing or something like that. I don't know. DLL 파일 때문에 죽는 경우 많지 않아요? Your program gets killed for missing DLL or corrupt DLL file and so on, right? So DLL file stands for dynamical linked library. So dynamical linked library. DLL file is a library file, but it's linked dynamically, meaning that at execution time instead of like at compile time. So linking occurs when the program begins execution. This is called dynamic linking. So here is a, you actually see this like code, the three different codes in one slide. The first one is original C code. This is source code, right? This is source code. And if you compile it, this line gets compiled into a move instruction. So move instruction is basically, this human readable form of machine code. And if you assemble it, you eventually get this machine code or object code, same thing. Okay? So what this C code does is store the value of t to the location pointed to by variable. Okay, that's the pointer, right? In assembly code, this one is realized by move instruction. So this one is like a source. This is destination. So here, the value of t is stored in register RAX, the storage like RAX, and you copy this value into the memory location pointed to RBX. So here are like, two operands. So t, the value of t is assumed to be stored in RAX register, and value of dest, like the pointer, is stored in RBX register. And you can use this move Q instruction with RAX, this is source, and this like parentheses. So parentheses means now you want to store this value into the memory location instead of the register itself. So if you don't have this parentheses, let's say you have like a RBX here, then what it does is you simply copy this value of RAX to the RBX register, right? But if you actually have this parentheses, then now this value of RBX is interpreted as a pointer. So now you actually copy this value into memory location pointed to by RBX register. Okay, so that's the difference. So move 8-byte value to the memory, and by using these parentheses, now you dereference the pointer. And this like instruction is translated into machine code, like 3-byte machine code 488903. So this one actually, this one is like interpreted by the CPU, like a hardware, as like this operation, and the CPU will execute this instruction. So this one is more like a more disassembled code. So in the previous like a sum store function, we actually had 6 instructions: push, move, call, move, pop, return. By the way, this Q thing, this one is suffix. I mean, this one means that this one is for like a legacy purpose. The Q is like a quad word, like it means like a 64 bits. So this one is like a, this code instruction, but the operand is like this one, like 64-bit version of the core instruction. And return is the same. I mean, this one is like a 64-bit version. And if you want to reconstruct this assembly instructions from the machine code, then you can use a special program called object dump. So the program, disassembler program does is, this is the opposite of assembler. So in this example, we actually have assembler program here, right? And this assembler does the opposite. So what this assembler does is it takes this machine code, ones and zeros as input, it reconstructs the human readable assembly code. This is called disassembler. And the object dump is the one like disassembler program. So once you execute in the command line something like object dump minus the sum, then it disassembles the function called sum. And to show like this, like assemble human readable instructions. And also alternatively, you can also use like a GDB. For like homework number 2, you'll have to use GDB a lot. So you better know how to use it, but we're going to give you some tutorial and so on. So GDB is very useful debugger. So when you debug your program. So once you use like a GDB, then you can execute something like disassemble like a sum store. Then this actually shows the assembly code of your function like a sum store. And this is another like example in GDB command. This one actually shows examine like a 14 bytes starting at sum store. This one actually shows this value, something like this. So this one, GDB, you learn more about GDB after you come back from Chuseok vacation. So, but hopefully you become very you familiarize yourself to this tool because it's really useful. I mean, for program debugging and so on. And also, if you use like object dump, you can actually also disassemble like a MS Word, for example. Like any EXE file can be disassembled. Because anything that can be interpreted as executable code can be disassembled. You can do some like reverse engineering. So once you actually know. You can really access the source code. You cannot really get the source code for MS Word, but you can still disassemble this like binary, code to obtain like assembly code. Then you can actually do some like hacking for this binary code. So disassembler examines this bytes and reconstruct assembly code from it. All right. So I think the time is up. So I think it's about the right time to stop. So if you have any questions, feel free to ask me. Otherwise, I'm going to see you guys on Thursday.